Hello, I'm Piotr Skrzypczyński. Welcome to the video presentation of a paper entitled Cross-modal transfer learning for segmentation of non-stationary objects using LiDAR intensity data. This is a paper presented at the ICRA 2020 workshop on sensing, estimating, and understanding the dynamic world. Let me introduce our research, why we would like to solve this particular problem. First of all, as you probably know, the sensor of choice for most of indoor localization systems is a 3D laser scanner, or LiDAR in short. It offers reliable measurements that are not affected by lightning and are also robust to weather conditions. Most of the LiDAR-based localization methods or SLAM methods register consecutive observations by using a variant of the iterative closest points algorithm, assuming that the observed scene is static and rigid. Those solutions are prone to errors caused by non-stationary objects. What we consider when we say non-stationary, we consider those objects that move or are in motion or can move, but also those that do not have rigid surfaces, such as tree canopies or grass shaken by the wind. When we encounter such an object in an environment using ICP algorithm and a laser scanner, we can have problems with ghost obstacles like this one that you can see on the screen that is marked by a blue rectangle. This problem is of particular importance in urban environments where vehicles, pedestrians, and vegetations can be disregarded for localization, as there are enough man-made static surfaces around for localization. So this paper is a study of methods that make it possible to detect and segment the non-stationary objects from LiDAR data in real time, involving very limited effort in the training and dataset preparation phase. Nowadays, deep learning methods are considered state-of-the-art in image segmentation. However, processing of LiDAR data using neural networks is still challenging. A problem is feeding the network with the LiDAR data. In contrast to the structure of images, point clouds are sparse and have a variable point density that depends on the range itself. So because of that, we cannot use very simple flat neural networks like for images. There are some neural network architectures that were designed purposefully for 3D point clouds, but they are suitable mostly for small point clouds, like for recognition of individual objects, and they cannot process all the points required for a modern, acquired from a modern LiDAR in real time. For example, we get about 2.6 million points per second from the recent OUSTER OS1 with 128 beams. These huge data streams require a special representation that should enable to use simple two-dimensional convolutions for neural processing to process this in real time, at least at the inference stage. A good representation in this case is a range image, which can be seen as a cylindrical projection of the points obtained from a rotating multi-beam scanner. You can see an example of such a range image on the screen in this moment. However, having such a representation, we still have one problem that remains. This is a problem with labeling. Because obtaining point-wise semantic annotations for 3D point clouds is labor-intensive and time-consuming, so there are few datasets that support this level of annotation. Of course, there are such data sets like a quite recent semantic kitty, but building such a data set as a semantic kitty requires a lot of effort and methods that make it possible to train a neural network without explicit ground truth labels on LiDAR data are investigated. They are in a very center of focus of our research community. So in this context, we propose a simple yet effective approach to supervised learning of LiDAR data segmentation and also unsupervised segmentation. In both, we exploit the intensity output, which is also called reflectancy, that is available in many of our 3D laser scanners, if not in all of them. But this sensing modality is really used for segmentation. So we try to investigate relatively unexplored area in semantic segmentation and in motion segmentation for LiDAR data. Our key insight is that modern LiDAR yields range and signal intensity which are spatially and temporally aligned, while the spatial density of those measurements makes it possible to consider the depth image as a low-resolution camera image. We make an assumption that the visual differences that allow us to distinguish different objects in grayscale images are to a large extent preserved also in the LiDAR intensity data. So our approach facilitates learning from standard grayscale images, which are commonly available with class and instance level point-wise annotations. How we produce those images from LiDAR data from point clouds. Typical LiDARs used for outdoor navigation, such as VELODYNE and OUSTER sensors, measure distances at selected horizontal and vertical angles, returning also the corresponding intensity values. A single scan can be represented as an image with each pixel mapped according to the angle increment of its corresponding laser beam, with results in a nonlinear projection. To facilitate cross-modal transfer learning, which is at the heart of our method, we represent LiDAR measurements as an image compatible with the grayscale camera images produced according to the pinhole camera model. So very, very typical images that are available in many datasets equipped from cameras. To this end, we divide the 360 degrees laser scan, like from a VELODYNE or OUSTER, into 6 horizontal parts, and then we define a virtual camera with the focal length, image center, and vertical field of view that depend on the LiDAR parameters. And at the end, we synthesize 6 artificial images from either depth or intensity data. However, the focus of this presentation is on intensity images. The image intensity for subpixel positions is computed using a linear interpolation of the neighboring pixel values, and an inpainting algorithm based on the fast merging method is also used to remove non-return areas in this image. On this slide, you can see an example of images synthesized using our methods. There's a comparison of directly generated laser intensity image, which is in the upper part, from OS1 with 64 beams, and the camera-like images, only 3 of them, are shown here for the same scan that were synthesized according to the method shown in a previous slide. How far are those images from a real grayscale images? As you can see on this slide, they are not so far from real images, even for a sensor with only 64 laser beams like a VELODYNE HDL 64. So we can use those intensity images in much the same way as grayscale images from regular camera. So let me proceed to our learning methods. Of course, we use the concept of transfer learning, and this is specifically cross-modal transfer learning with the synthesized intensity images, which is implemented in two variants, a supervised one and unsupervised one. The supervised version is aimed at real-time semantic segmentation that demonstrates the usefulness of grayscale images commonly available with pixel-wise annotation for our approach for cross-modal learning. Specifically, we use images from Kitty and Cityscapes datasets mostly, also a couple of different sets of images also were used. For this purpose, we try to make this learning set as diversified as possible. What we had to do with those images to make it possible to learn for a cross-modal system. Original class labels are merged into three classes. The stationary objects like a road, building, wall, traffic sign, and so on. Those that are possibly stationary objects like cars that can stand at the street or they can be in motion, also trucks, and the vegetation that can be shaken by the wind or not. We can decide if it makes sense to delete those pixels that belong to vegetation or not. And the last category are those objects that are definitively non-stationary, like persons, pedestrians, bicycles, and motorcycles. Generally, those objects are small and do not provide good anchors for localization, even if they are stationary for a moment. So those three classes are easy for classification, but in comparison to binary classification, so only into non-stationary and stationary, this approach facilitates flexible point rejection strategy in a localization system. However, learning with only those grayscale images is not enough. This approach has some drawbacks. First of all, the modern convolutional neural networks are designed for high-resolution images, while our synthesized intensity images have a much lower resolution. Moreover, in typical data sets, only images from a frontal camera in a vehicle are available, while the LiDAR covers 360 degrees field of view, so we need a method to learn how to detect moving objects in the back, on the left, on the right, and so on, not only in the front. Therefore, we use also intensity images synthesized from LiDAR data for learning. Those images were manually labeled according to our three-class segmentation scheme. And we also have implemented an unsupervised approach that uses the weights learned from typical video sequences only in the pre-learning stage, but then learns directly from the synthesized images that cover the full field of view of the LiDAR. So let me talk specifically about the neural architectures used in our system. There are two parts of this approach. The first one concerns the supervised learning. For supervised learning, we employ the recent very efficient ERFnet architecture. This supervised cross-modal learning is implemented in two stages. At first, the ERFnet is pre-trained on 10,000 labeled images from well-known datasets that were mentioned before. The training images and labels need to be processed to resemble the synthesized intensity images. The images are converted to grayscale and rescaled, while the original class labels are merged into those three classes are already mentioned before. So in the second stage, the ERFnet model is fine-tuned on only 150 intensity images synthesized from the publicly available OS1 sequences, and those images were manually labeled according to our three-class segmentation scheme. I have seen example in one of the previous slides, and the network model trained this way is used for real-time inference in intensity images. It works in real time on a commodity GPU hardware. So the second approach aims to directly segment the synthesized intensity images into regions with non-stationary objects and the background, and this is the unsupervised approach. We use the competitive collaboration framework, which is a pretty recent neural network architecture that actually consists of 4 separate networks designed for different tasks. That is disparity estimation, optical flow estimation, camera pulse estimation, and motion segmentation. Authors of this framework provided network weights for all models trained on kitty RGB images. The architecture of disparity network is inspired by DispNet, and the optical flow network is inspired by FlowNet. The camera motion prediction network is a simple stack of convolutional layers, while the motion segmentation model is an encoder-decoder architecture, which is similar to UNet. How this approach works? This architecture defines 2 players and a moderator. The first player consists of a depth and camera motion networks that reason about the static regions in a scene. The second player is an optical flow network that reasons about the moving regions. For training the competitors, the motion segmentation network selects those networks that are here marked with D and C on pixels that are static, and selects the network F on pixels that belong to moving regions. In the second phase of the training cycle, the competitors collaborate to reason about static scene and moving regions by forming a consensus that is used as a loss for training the moderator. We adapted the existing weights as cross-modal transfer knowledge, and then we only fine-tuned the motion segmentation model on intensity images synthesized from the kitty dataset. In order to have a full coverage of the LiDAR's horizontal field of view, we trained 6 separate motion segmentation models for each 60-degree field of view. Each model was trained in an unsupervised way on 15,000 of intensity images. The motion segmentation network takes as input a set of 5 consecutive frames, and the output mask is generated for the 3rd frame in sequence. The output is a continuous grayscale soft mask representing motion segmentation. To decide whether a point should be rejected or not, we have to apply a threshold to this output and generate a binary mask. Although we do not have a different classes of non-stationary objects in this case, we still can decide on the amount of non-stationary points we want to reject in the localization module. In the last slide in this section, you can see results of this unsupervised learning of motion segmentation. The network correctly detects cars passing in front of the sensor, but also those moving in the sides out of the field of view of a typical frontal camera using VELODYNE data. If we use OUSTER images synthesized from OUSTER data, it is also possible to segment smaller objects like pedestrians and even some bicycles. So the target application of our approach is obviously simultaneous localization and mapping. For this purpose, we use LOAM. LOAM means LiDAR odometry and mapping. This is a very popular algorithm that is pretty accurate on estimation of the trajectory. This algorithm combines scan-to-scan real-time odometry and registration of the LiDAR scans to an incrementally updated point-based map. LOAM tries to select stable features for matching using only points that correspond to sharp edges or planar surface patches. The edges and planar patches are identified in the point cloud using a simple smoothness criteria, which considers the Euclidean distance between neighboring points. While this heuristic rejects some measurements that are potential outliers in the ICP matching, it is generally insufficient in environments with many non-stationary objects. So we want to modify this architecture, a LOAM architecture, adding our filter mask. Of course, we take into account that the LiDAR yields a range and intensity which are spatially and temporally aligned. So we can define a mask that makes it possible to filter out the points that cannot be trusted for localization. The inference is real-time on the laptop with a commodity GPU card. So the system still works at the same speed as before, as the original LOAM. So how we evaluate the LOAM system with our modifications? We evaluated this approach on data from two types of LiDARs, the VELODYNE with 64 beams using data from the Kitty dataset, and the two variants of OUSTER OS1, namely the 64 beams variant and the 128 beams variant, or scan lines variant, to verify whether rejection laser points that belong to dynamic objects improve localization accuracy in LOAM. The Kitty dataset was used because these datasets provides ground truth from the GPS or RTK GPS. So you can see an example of motion segmented intensity images on this slide. From a VELODYNE, we have 6 of those images. And then you can see the map of points that was produced by LOAM, an unmodified version, and a version in which you can see the points that are detected as belonging to a non-stationary objects. So the quantitative data are shown in this table as a comparison between our approach and the original LOAM. As you can see, our approach improves results in all those trajectories that were used for evaluation. We have used 3 trajectories, those that were not used previously for learning. Of course, the amount of improvement depends on the number of detected non-stationary objects in a given sequence and on an environment type in which the scans were recorded. So let me show you a short movie that presents our approach on a data set of better resolution coming from the OUSTER OS1 scanner with 128 beams. Unfortunately, for this data set, we do not have a ground truth, so only qualitative results can be presented, like in this slide. We can select those points then belong to moving objects. They are the red points in this point-based map of the LOAM system. This is a single scan as seen by the sensor after our mask or filter. And then how it looks in a point-based map of LOAM. As you can see, if we do not remove those points, the objects corrupt the map with spurious points. You can see a long trail left by the large truck that was moving during this crossing. And if we apply our method in input of a LOAM system, actually, as you could see on the block diagram before, we can get rid with this problem. We no longer have this wake of spurious points in the map. Of course, this approach is not perfect. Sometimes we fail to detect some objects like this guy on a bicycle that was perhaps too close to our LiDAR for providing reliable intensity measurements to the system. So there is still a room for improvement. And so let me conclude this presentation. The contribution of this paper is the demonstration how LiDAR intensity data, which is often neglected for robot navigation, can be helpful in dynamic environments by allowing rejection of points that are related to non-stationary objects. This goal is achieved using a simple procedures of synthesizing intensity images from raw laser measurements and applying cross-modal transfer learning to conserve manual effort and time when preparing the training data. We think that this approach is of practical value, as instead of a low effort training, our approach can segment the intensity images at the sensor scanning rate, serving as a filter on the input of a SLAM system. So also a short outlook for our further research. We will try to show if it is practical to work with multi-channel synthesized images, so using together depth and intensity for inference on moving objects, perhaps also for semantic segmentation. We also try to adopt different deep learning frameworks and test them with our synthesized intensity and perhaps multi-channel images. So thank you for your attention.